Let's start with proving part 1 of this result here. So assume f is any function of sets from a set x to a set y, and assume that script b is any sigma algebra on y. And we have now defined this collection of subsets of x. The preimages of all the elements of the sigma algebra script b. Again, usually elements of a sigma algebra are called measurable sets, just like elements of a topology are called open sets. So this is the collection of preimages of all the measurable subsets of y. Then our goal is to prove this is a sigma algebra. So we have 3 things to prove: that it contains the empty set, that it's closed under countable union, and that it's closed under complement. So first, why does it contain the empty set? Well, the preimage, the empty set, so let's start this way. The empty set is the preimage of the empty set, right? And that the empty set that you're seeing here is one of the possible b's. It's a measurable subset of y. So that's it for that. That was easy. Now for countable unions. So let's assume an, and I'm using the letter A, Roman A, because this is going to be referring to some subsets of capital X here. So that's the convention I'm trying to follow to help you keep track of things, is A-type things, script A or Roman A, are going to be related to here, and B-type things related to there. So assume the A sub n's that is a sequence of measurable subsets of y, so of elements of script B. Sorry, is a sequence in here, is what I should do. I'm trying to show this is closed under countable union. Well, then each one of these is the preimage of a measurable subset of y, right? So for each n, so I'm using countable choice, I guess. For each n, a sub n is the preimage of, let's call it b sub n. For some b sub n measurable. Then, now our goal is to show that the union of all the ANs is in here, right? So the union of the ANs is the union of preimages of BNs, but the union of some preimages is the preimage of the union. So we can do this. And the union of the BNs, since the BNs are all measurable subsets of y, they're all elements of this sigma algebra, their countable union is as well. That's part of the definition of sigma algebra. So since this union is in here, we've now realized this set as the preimage of something measurable, some measurable subset of y. So that proves that that set is in the pullback of the sigma algebra on y. All right, so 2 of 3 properties are checked off. We got the empty set, we got closure under countable unions. Now finally, complements. So assume A is in there, in the so-called pullback of the sigma algebra on y. Then can we prove that the complement is? Well, then the complement of A is, first let's unpack what it means for A to be in there. It means A is the preimage of some B. measurable. So in the sigma algebra on Y. So the complement of A is the complement of a preimage. And preimages are just awesome. Complement of a preimage is the preimage of a complement. Of course, here the complement is with respect to Y. So what's in this property of preimages that I'm using, this needs to be the domain of F, and this needs to be the codomain of F, which they are. And are we done? Yeah, since the complement of B, that's the complement of a measurable set, so it's measurable. Again, by measurable, I would just mean in the sigma algebra. So the complement of something in a sigma algebra is in the sigma algebra. We have realized this as the preimage of something in script B. So it is in the pullback of script B. Great, so that verifies closure under complements. So with these three things checked, we have now proven part one of this result, that if you try to pull back a sigma algebra on Y by doing this, by taking preimages, then that does indeed give you a sigma algebra on X.